Have you ever been on a plane, felt that incredible push as it accelerates down the runway, and just for a moment thought about the sheer ingenuity involved?
That rumble, yeah. That surge of power.
It's far more than just a big metal tube moving through the air, isn't it? It's like this whole hidden universe of complexity at play.
Absolutely.
Welcome to the Deep Dive. Today, we're peeling back the layers on that very topic, the fascinating world of aviation propulsion. We're going to really dissect turbine engines, how they're designed, their intricate systems, and the basic physics that literally lift them into the sky.
And for this deep dive, our source material is, well, it's pretty serious stuff. It's an EASA Part 66 Module 14 training manual on propulsion.
The kind of thing maintenance techs study.
Exactly. It's dense, highly technical material for aircraft maintenance technician certification. But our mission today for you is to kind of distill it. We want to pull out the most crucial insights, maybe some surprising facts, those aha moments that turn a dry manual into something, engaging.
Okay, let's unpack this. Let's start right at the foundation. The fundamental physics that underpin how these massive engines actually work. It all kicks off with energy. We're talking about two main types here. First, potential energy.
Right, the stored stuff.
Yeah, energy at rest, basically, like water sitting high up in a reservoir, or maybe a stretched bungee cord just waiting to snap back. And in aviation. Think aviation gasoline. It's truly remarkable stuff.
The numbers are pretty wild.
1 pound of aviation gas contains a staggering 18,900 BTUs of heat energy. That's enough potential to perform, get this, 14,704,200 foot-pounds of work.
Just incredible energy density.
Then, of course, there's kinetic energy. That's just energy in motion.
Simple enough.
Yeah, the airplane rolling down the runway or the engine parts spinning like crazy.
Yeah.
Same fundamental concept as potential, just, converted into action.
And harnessing all that energy brings us straight to Sir Isaac Newton's laws of motion. These aren't just textbook ideas. They are absolutely fundamental to how a jet engine works. His first law, the law of inertia. Objects at rest stay at rest. Objects in motion stay in motion.
Unless something pushes or pulls them. Like when the plane brakes suddenly and you lurch forward.
Exactly. That's your body resisting the change in motion. That's inertia. Okay, the Newton's second law, this is where we really start talking propulsion. Force equals mass times acceleration, or FMA.
Right, momentum. Like a big, heavy train is hard to stop even if it's moving slowly.
Precisely. It's got huge mass. For a jet engine, this law gives us the actual formula for thrust. So imagine a turbojet engine, right? Maybe it moves 150 pounds of air every single second. And it accelerates that air from, say, 100 feet per second up to 1,200 feet per second. That huge acceleration of mass creates 5,124 pounds of thrust. It's just raw acceleration of mass.
Oh.
And then the famous third law, for every action, there's an equal and opposite reaction.
This is the core of it, right? How the engine actually moves the plane.
It is. And there's a common misconception here. People sometimes think the engine pushes against the air behind the plane.
Like rowing a boat?
Kind of, but that's not quite it. Instead, the engine sucks in air, accelerates it like crazy, and throws it backwards really fast. That's the action.
Okay.
And the reaction is the engine itself and the whole aircraft being pushed forward. That reaction force is thrust.
Okay. The rocket example helps here.
Perfect example. A rocket in space works fine. There's no air to push against, but it throws mass out the back, action, and moves forward, reaction.
Got it. That clarifies it perfectly. So energy, Newton's laws. What about airflow itself? That brings us to Bernoulli's principle, yeah?
Yep, Daniel Bernoulli. His principle describes how fluids, including air, behave when they flow through changing areas.
Like a tube that gets narrower in the middle.
A venturi.
Exactly, a venturi. As the air speeds up through that narrow bit.
Its static pressure goes down. Kind of weird, but okay. It seems counterintuitive, but yeah. Velocity up, static pressure down, the total pressure stays the same. It just shifts between static and dynamic, or velocity pressure.
And this is huge in aviation.
Absolutely fundamental. It's how a wing generates lift, faster air over the top, lower pressure, pulls the wing up.
Okay.
And it also explains why a subsonic engine inlet, the duct leading to the compressor, is actually diverging, getting wider.
To slow the air down.
Right. Slow the air, increase its static pressure before it hits those compressor blades. It's all about managing the airflow, precisely.
Like an invisible dance happening constantly.
It really is. And what's fascinating is how these principles, energy, Newton, Bernoulli, they all work together. We also need to touch on Boyle's and Charles's law.
Gas laws, right.
Yeah.
Pressure, volume, temperature.
Exactly. They describe how those three things relate for a gas. Squeeze a gas, compress it, its pressure goes up, volume goes down, temperature tends to rise.
Like in the engine's compressor section.
Perfect. Then, in combustion, you add fuel and heat, massive increase in temperature and pressure. Volume expands hugely,
Driving the turbine.
which then drives the compressor. And as the gas exits, pressure and temperature drop, volume increases. It's this continuous cycle of pressure, volume, and temperature changes governed by these laws that actually generates the power.
A controlled transformation, like you said.
Yeah.
Okay, so let's shift gears from the physics principles. Here's where it gets really interesting. The engines themselves.
The hardware.
Right. Now, a key thing about gas turbines, different from old piston engines, is they have separate sections doing different jobs all at once.
That's a crucial difference. You've got the air inlet, the compressor section, then combustion, the turbine section, the exhaust, and the accessory gearbox, all working continuously and simultaneously.
And we talk about a cold section and a hot section.
We do. Basically, everything from the inlet through the compressor is the cold section, relatively speaking, of course.
And the hot section starts at the combustion chambers.
Right. Combustion, turbines, exhaust, that's the hot section. Very, very hot.
Okay. So what are the main types of these gas turbine engines we see flying?
Well, in aircraft propulsion, there are really 4 primary types we need to talk about. First, the original, the turbojet.
The ancestor.
Pretty much. But you don't see many pure turbojets on commercial planes now. They're noisy, and they tend to guzzle fuel, especially at the speeds airliners fly, around Mach 0.8.
And in a turbojet, all the air goes through the engine core.
100%. Every bit of air goes through the compressor, combustion, and turbine.
Okay, so what replaced it mostly?
The real workhorse today, especially for air transport, is the turbofan. This is where things get clever.
The ones with the huge fans at the front.
Exactly. That massive fan produces most of the thrust, maybe around 80%, by just moving a huge amount of air around the engine's core. It bypasses the core.
Hence bypass.
You got it. And because it's moving a large volume of air more slowly compared to a turbojet, it's much quieter and way more fuel efficient, particularly at those high subsonic speeds. These often have multiple spools, 2 separate rotating shafts, a low-pressure spool for the fan and initial compression stages, and a high-pressure spool for the later compression and turbine stages. That high-pressure core is often called the gas generator.
So that bypass ratio, the amount of air going around versus through the core, that sounds critical.
Oh, absolutely critical. Bypass ratio is key. High bypass turbofans, like on your typical airliner, have a large ratio, moving lots of air around the core. Very efficient, quiet.
And low bypass.
You find those more on military jets. Less air bypasses the core. They might need raw speed or power, and sometimes they even have augmenters or afterburners.
Where they dump extra fuel into the exhaust?
Yeah. Right, for a massive temporary thrust boost. Very thirsty, but effective for combat or takeoff. But the beauty of the turbofan, especially high bypass, is converting fuel energy into pressure more efficiently, pushing a larger mass of air. More thrust, better fuel economy, longer range. It's a win-win for airlines.
That makes total sense. Okay, type 3.
Type 3 is the turboprop. Here, the gas turbine engine doesn't just produce jet thrust. Its main job is to turn a propeller.
Through a gearbox, right, to slow the speed down.
Exactly, a speed reduction gearbox. Turboprops are super efficient for planes flying in the, say, 300, 400 mile per hour range. And they're great for using shorter runways.
And most of the energy goes to the prop.
Yeah, something like 80–85% of the energy drives the propeller. The rest comes out as exhaust thrust, but the prop does the heavy lifting.
Okay, and the last one.
The turboshaft. This is similar to a turboprop, but instead of driving a propeller, the engine's power is delivered to a shaft.
For helicopters.
Primarily, yes, driving the main rotor and tail rotor, but also used for auxiliary power units, APUs, on larger aircraft.
Right, the APU provides power on the ground.
Yep, electrical power and bleed air for air conditioning and engine starting without running the main engines. It's essentially a small turboshaft engine tucked away somewhere, usually in the tail cone.
Got it. 4 distinct types for different jobs.
Yeah.
But across all of them, there must be some universal things they all need to achieve, right? Some general requirements.
Absolutely, that's a great point. Regardless of type, every aircraft engine has to meet stringent requirements. Efficiency and economy are huge fuel burns, sure, but also purchase price, maintenance costs.
Reliability has to be paramount.
Non-negotiable. They need to perform consistently at their rated power in all sorts of conditions, different altitudes, weather, durability too. How long can it run before needing a major overhaul? That's TBO, time between overhaul.
What about flexibility?
Operating flexibility, yeah. running smoothly from idle all the way up to full takeoff power across a wide range of temperatures and pressures. And finally, compactness. They need to fit neatly, allow for streamlining, good pilot visibility, and stay within weight limits.
It's a tough balancing act. Efficiency, reliability, durability, cost.
It drives incredible complexity in the systems, especially when we start talking about control.
Yeah, let's go there. The fuel systems. You called them the brains of the engine earlier. It sounds like they do way more than just pump gas.
Oh, much more. Controlling fuel flow precisely is everything. You need to adjust constantly for changes in air temperature, pressure, altitude, pilot demand. It's a monumental task.
And getting it wrong is bad.
Very bad. Too much fuel for the air available, you get a rich blowout, the mixture cools too much, the fire goes out, engine stalls.
And too little fuel.
Lean flame out, not enough fuel to sustain combustion, fire goes out again. So the system has to meter the exact right amount of fuel.
And not just the amount, but how it's delivered.
Exactly. Fuel atomization is critical. You need a fine, mist-like spray for efficient burning, not, a dribble or large droplets.
So how have these controls evolved? You mentioned 3 basic groups.
Right. The oldest were purely hydromechanical. Think complex clockwork using engine speed, air pressure, and mechanical linkages to figure out fuel flow. No electronics involved. Less accurate, especially under changing conditions.
Then came electronics.
Sort of a hybrid stage. Hydromechanical electronic. Here you still had the basic mechanical system, but an electronic engine control unit, an EFCU or EEC, would trim the fuel flow, fine-tuning it based on more sensor inputs.
With the mechanical part as a backup.
Exactly. The EEC would send signals to a torque motor on the fuel control, making small adjustments. But if the electronics failed, the hydromechanical part could still manage the engine, just maybe not as efficiently. It controlled pumps, valves, metering, responding to the power lever.
Okay, and the state-of-the-art now?
Is FADEs, full authority digital electronic control. And what's really fascinating here, the defining feature, is that a true FEE system has no hydromechanical backup.
Wow, really?
Yeah.
It's all in on the electronics.
Completely. The EEC, the computer, takes total control. It gathers data from electronic sensors all over the engine speeds, temperatures, pressures, and directly commands a fuel metering valve.
That sounds risky. What if the computer fails?
That's why they have redundancy. FADC systems are dual-channel, 2 identical computers running in parallel, constantly checking each other. If one channel has a problem, the other takes over seamlessly.
Okay, that makes more sense. And power.
They can run off the aircraft's electrical system, but often they have their own dedicated generator built into the engine, a permanent magnet alternator or PMA. So even if the aircraft loses all electrical power, the engine's FADC keeps running.
Smart. And it does more than just meter fuel.
Oh, yeah. It optimizes performance, limits engine parameters to prevent damage, stores tons of performance and maintenance data, manages starting sequences. It's incredibly sophisticated, usually has a primary control mode, often EPR-based, and a backup mode, maybe N1-based.
So FADTC sounds like a huge leap. Any downsides apart from that reliance on electronics?
Well, that reliance is the main consideration. The pilot loses that direct mechanical linkage. You're trusting the software and hardware. But the upsides, efficiency, safety margins, reduced workloads, smoother operation, better diagnostics are just immense. It really changed engine management.
Okay, so let's dig into some of the actual components in these fuel systems. The nuts and bolts.
Sure. You start with the main fuel pumps, usually engine-driven, providing continuous fuel flow at the right pressure. Could be constant displacement, always pumping a set amount, or non-constant adjusting flow to demand. They'll have relief valves to handle excess flow.
And after the pump, you mentioned fuel heating.
Right, the fuel heater, super important. Jet fuel can have tiny amounts of dissolved water. Below freezing, that water forms ice crystals, which can clog fuel filters fast.
So the heater prevents that.
Exactly. It uses hot engine bleed air or hot engine oil in a heat exchanger to warm the fuel just enough to keep ice from forming, or even thaw if it has formed. There's usually a warning light if the filter starts clogging. FADC systems can even automate this, controlling the temperature precisely.
Okay, heated fuel then goes to filters.
Yep, fuel filters, usually a low-pressure one before the pump and a high-pressure one after. Often micron filters catching incredibly small particles, like 10-25 microns.
Tiny.
Very. These filters often use cellulose, which also absorbs water. Because they can clog, they must have a bypass valve. If the filter gets totally blocked, the valve opens so fuel can still get to the engine even if it's unfiltered for a bit.
Which is why keeping water out of the tanks is so important. Daily sump draining.
Absolutely critical maintenance task.
Okay, filtered, heated fuel. Now it needs to get sprayed into the combustor.
Right. Through the fuel spray nozzles and manifolds, their job is to inject that fuel as a very fine, atomized mist in a precise pattern. Even spray, even burning, prevents hot spots that could damage the engine liner.
Different types of nozzles.
Yeah, older engines might have used simplex nozzle, single manifold. More common now are duplex nozzles. They give a better spray pattern over a wider range of fuel pressures, but they need a flow divider.
What does that do?
It splits the fuel into a primary flow for starting and low power and adds a secondary flow through separate orifices in the nozzle at higher power demands. Gives good atomization across the board.
Clever. Any other types?
Air blast nozzles are more advanced. They use airflow within the nozzle itself to help atomize the fuel even better. Operate at lower fuel pressures, reduce carbon buildup.
Okay, and valves to stop the fuel flow cleanly.
Exactly. Fuel pressurizing and dump valves. The pressurizing valve maintains pressure in the system, but ensures a sharp cutoff when the engine shuts down. No dribbling fuel into the hot engine.
Which prevents fires or carbon.
Right, after fires or coking. And related are combustion drain valves. These automatically drain any unburnt fuel from the combustion cans after a shutdown or a failed start sequence. Prevents a hot start next time you try to light it.
Makes sense. What about knowing how much fuel you have left?
Fuel quantity indicating units. Usually fuel counters or totalizers. They show remaining fuel, typically in pounds or kilos. Useful, but pilots know they can be slightly inaccurate if, say, fuel was jettisoned or there's a leak somewhere before the engine. It's more for overall awareness.
Okay, that's a really complex system just for fuel delivery. It's clear how vital precision is. But with all that happening inside, how do pilots actually keep tabs on the engine's health? The indicating systems must be critical.
Absolutely critical. They need to be reliable, accurate, and crucially, show information pretty much instantaneously. Like you said, imagine a lag on the EGT reading.
Yeah, exhaust gas temperature. You could overheat the turbine before you even knew it.
Exactly. So cockpit instruments generally fall into two buckets. Engine operation showing performance, like thrust, and engine monitoring showing health, like oil pressure, temperature.
And they're usually grouped together in the cockpit.
Typically, yeah. Center panel, maybe slightly biased to the captain's side. Thrust indicators, the primary performance gauge, are almost always right at the top. Easy to see.
How are these things displayed? Still old dials.
You still see analog indicators, the classic pointer on a dial in older aircraft or its backups, but mostly now it's digital indicators. Either simple numerical readouts or, more commonly, graphics on electronic displays, CRTs or LCDs, the glass cockpit.
Which are better?
Generally, the electronic displays are more reliable, more accurate, and can consolidate data from multiple older gauges onto one screen. They do often need cooling, though, but the key thing, regardless of type, is the use of colored zones.
Green, yellow, red.
Universal standard.
Green, normal operating range.
Yeah.
Yellow, caution, monitor closely, maybe time-limited operation. Red, danger zone, unacceptable, requires immediate action. It's instant visual communication.
Smart. Okay, let's talk specific operating parameters. How do pilots see thrust?
Two main ways. EPR, engine pressure ratio. That's the ratio of pressure leaving the turbine to pressure entering the engine. It's a direct measure of the engine's work on the air.
Pros and cons. EPR is often considered very accurate, a true measure of thrust. But the sensors can be a bit delicate, prone to icing or damage, and there can be a tiny lag in the reading.
And the other way.
N1. That's the rotational speed of the low-pressure compressor, the big fan at the front, shown as a percentage of its maximum RPM.
And that's more responsive?
Generally, yes. N1 responds very quickly to power lever changes and is quite stable. On many aircraft, N1 becomes the primary thrust setting reference, especially at lower altitudes or for certain procedures.
Okay. Then you mentioned EGT, exhaust gas temperature. Critically important, you said.
Hugely important. It's the best indicator we have of the temperature inside the turbine section, which directly impacts engine life and integrity.
But it's not measured at the absolute hottest point.
Right. The hottest point is just entering the high-pressure turbine, but sensors wouldn't last there. So EGT is measured downstream, maybe between the high and low-pressure turbines, or just after the low-pressure turbine. It's a representative temperature.
How's it measured?
With thermocouples, usually K-type, Cromel, and LEMO wires. Several are placed around the exhaust path and connected in parallel to give an average reading and provide redundancy. It's the engine's fever thermometer.
Got it. What else for operation?
We also monitor N2, the speed of the high-pressure compressor rotor, again, as a percentage, and FF, fuel flow, shows the rate the engine is burning fuel, usually in kilos or pounds per hour.
And that measures mass flow, not volume.
Crucially, yes, because fuel density changes with temperature, but the mass of fuel contains the energy, so the engine control and performance calculations need mass flow rate.
Okay, those are for operating the engine. What about monitoring its health?
Key monitoring parameters include the lubrication system. Pilots watch oil quantity in quarts or liters, oil pressure, PSI, and oil temperature. You get alerts for low oil pressure, obviously.
Any warnings for filters clogging?
Yes, often a two-stage warning for the oil filter. A first alert says it's starting to clog, then a second if it's bypassing. Gives maintenance a heads up.
What about vibrations? Can you detect if something's going wrong mechanically?
Absolutely. Engine vibration indication systems use accelerometers, often piezoelectric crystals mounted on the engine casing.
They sense shaking.
Exactly. They feed data to an engine vibration monitoring unit, EVMU. It analyzes the signals, indicates vibration levels, and can trigger alerts if limits are exceeded. It's an early warning for potential bearing failures or fan imbalances.
Anything else monitored?
Nacelle temperature. Not strictly an engine parameter, but sensors in the engine cowling alert the crew if temperatures get abnormally high in there. Could indicate a hot bleed air leak or maybe even a fire starting.
A secondary warning sign.
Right. Then, for turboprops and helicopters, engine torque is vital. It directly shows the power being delivered to the propeller or rotor shaft, measured hydraulically or using magnetic sensors, directly relates to horsepower and has strict limits.
And manifold pressure, MA.
Used mainly on piston engines, but also sometimes referenced with turboprops having constant speed propellers. It's the absolute pressure in the intake manifold, a direct indicator of how much power the engine is trying to make. Again, strict limits apply.
So these parameters aren't just displayed, they're used by other systems too, these interfaces you mentioned.
Oh, definitely. They're interconnected. Fuel and oil temps go to the EEC for controlling heat exchangers. N1 might be used for thrust control in alternate modes. Vibration signals might feed into automatic balancing systems.
And N2.
N2 is used heavily by the EEC for fuel scheduling, but also for things like controlling turbine case cooling, triggering auto reignition systems if the engine flames out, providing data for cabin air systems, electrical generators, hydraulics. It's a key input for dozens of things. Fuel flow data goes to the flight management system for range calculations. Low oil pressure might trigger automatic actions. It's a whole network.
Like the engine's nervous system talking to the rest of the aircraft's body.
That's a good way to think about it.
And how are pilots alerted if something goes wrong? Beyond the colored zones.
Monitoring and alert systems have evolved too. Older planes had warning lights built into or near the gauges. Modern glass cockpits centralize alerts on the electronic displays, MFDs. You get the colored indications, but also specific messages, often prioritized.
Audible alerts, too.
Yes, distinct sounds for warnings, most critical, versus cautions. And usually there's a central master warning or master caution light right in the pilot's primary field of view that illuminates, drawing their attention immediately to the specific alert message.
Okay, last thing here. Maintenance of these indicating systems. They sound pretty complex themselves.
They are. While the electronic displays in the cockpit are generally very reliable, the sensors out on the engine live in a brutal environment. Extreme heat, cold, vibration, pressure.
So they're often the source of problems.
They can be, yeah. Troubleshooting might involve checking thermocouple connections for EGT issues, looking for tiny air leaks in the EPR sensing lines, making sure vibration sensors are torqued correctly, or checking the gap between N1 or N2 speed sensors and their targets. It demands real precision.
What an incredible journey we've taken today. From, basic physics like energy and Newton's laws, through all the different engine types, the incredibly complex fuel systems like FADEC, and then how pilots actually monitor these beasts in real time. It really is mind-boggling.
It is. So what does this all mean for you listening? It means every time you hear that engine spool up or feel that push during takeoff, you're experiencing just layers upon layers of human ingenuity and precision engineering. It's taking fundamental physics and applying it with incredible sophistication to achieve something as amazing as reliable, efficient flight.
Yeah, and it's a constant reminder, isn't it? Despite these incredible leaps in automation, like FADs taking over so much control, the basic, unchanging laws of physics, and the diligent, often unseen work of human maintenance crews, checking those sensors and systems, they remain absolutely critical. Safety and reliability still depend on understanding those fundamentals and ensuring the hardware is perfect. So, Thinking about everything we covered, what unexpected layer of complexity or maybe even simplicity did you find most striking today? Something to ponder until our next deep dive.